Alkanes have fairly limited reactivity, but they can be halogenated using chlorine or bromine under free radical conditions to produce alkyl halides. This provides an important entry into other reactions because the halogenation of the alkane functionalizes it. This reaction proceeds through radical intermediates. A radical is a species with an unpaired electron. As we draw radical mechanisms, the mechanistic steps will be divided into three categories: initiation, propagation, and termination. And as we draw these mechanisms, we will use fishhook arrows or single barbed arrows to show the movement of single electrons. This is in contrast to the typical mechanistic arrows that describe the flow of two electrons. Radical reactions begin with initiation steps, during which the active radicals for the rest of the mechanism are produced. When exposed to heat, as abbreviated by a capital Greek delta, or light, as abbreviated by h nu, a few molecules of chlorine or bromine, represented generically below as X2, will homolyze. When they do, the halogen-halogen bond breaks evenly, with one electron moving on to each halogen atom. What follows are the propagation steps, which begin and end with radicals. In propagation step 1, a halogen radical abstracts a hydrogen atom from the alkane. This occurs when the halogen uses its single electron to begin to make a sigma bond to a hydrogen from the alkane. The hydrogen reciprocates, bringing an electron with it, and the remaining red electron is deposited onto the carbon to make a carbon-centered radical. During propagation step 2, the carbon-centered radical abstracts a halogen atom from an unreacted molecule of X2. During this step, two very important things happen. The product of interest, the alkyl halide, is created, and the active radical is regenerated. These observations have two important consequences. The first is the realization that the vast majority of product is formed during propagation step 2, not in the termination steps. Secondly, since the radical is regenerated, it can cycle back into the first propagation step, which makes this a chain reaction that continues until all of the reactants are consumed. Termination steps merely explain the fate of the few radicals remaining after almost all of the reactants have been consumed. In termination steps, any two radicals can combine. But it's important to remember that nearly all of the product is generated as a result of propagation step 2. As a result, the termination steps are fairly inconsequential when you're trying to explain the formation of the major organic product. In this specific example, cyclohexane will be chlorinated. The reaction begins with the homolysis, or the even cleavage, of the chlorine-chlorine bond when it is exposed to heat or light. The chlorine radical then abstracts a hydrogen atom from cyclohexane. All of the hydrogen atoms of cyclohexane are equivalent, so any one can be abstracted, leading to the same reaction product. Hydrochloric acid is formed as a byproduct of propagation step 1. In propagation step 2, the cyclohexyl radical will abstract a chlorine atom from an unreacted molecule of Cl2. This forms the product, cyclohexyl chloride, and it regenerates that active chlorine radical, which can continue to cycle back into subsequent propagation steps. In general, free radical chlorination is only used when a single chlorination product is possible. Chlorination suffers from low selectivity because both of its propagation steps are exothermic. And so when more than one chlorination product is possible, mixtures often result from free radical chlorination. On the other hand, Bromination is a much more selective process. Free radical bromination has an endothermic first propagation step and an exothermic second propagation step. The highly exothermic nature of the second propagation step makes the process favorable. The endothermic nature of the first propagation step leads to selectivity in the formation of only the most stable carbon-centered radical. In this specific example, we'll consider the bromination of methyl cyclohexane. This reaction begins with the homolysis of bromine upon exposure to heat or light. In propagation step 1, the bromine radical abstracts a hydrogen from the only tertiary carbon in the molecule. This leads to the formation of only the most stable tertiary carbon-centered radical. During propagation step 2, the tertiary radical abstracts a bromine atom from Br2, yielding the tertiary alkyl bromide product. The bromine radical is also regenerated, which allows this to cycle through another round of propagation, making it a chain reaction. Stereochemistry may be an issue during certain radical reactions, so it's important to recognize that radicals are sp2 hybridized and therefore have trigonal planar or flat geometry. Consequently, if a stereocenter is formed during a radical reaction, both configurations will be produced at that center. Let's consider the bromination of 3-methylhexane, which begins with the homolysis of bromine. During propagation step 1, the bromine radical will selectively remove the hydrogen from the only tertiary center in the molecule. This affords a stable tertiary radical. During propagation step 2, the radical abstracts a bromine atom from Br2, and during this step, a stereocenter is formed. Since the radical has trigonal planar or flat geometry, the bromine atom can add from either side, yielding a racemic mixture of products in this instance. In the previous example, the reactant contained a stereocenter, but its stereochemistry was unspecified. It's useful to note that even if we specified a particular stereochemistry in the reactant, the result would be the same, because the intermediate radical has trigonal planar or flat geometry and is therefore not a stereocenter. When the bromine atom adds, it again adds from either below or above to generate a racemic mixture of product. In summary, radical halogenation converts an alkane to an alkyl halide by treatment with chlorine or bromine in the presence of heat or light to initiate the process. Chlorination is most useful when only a single alkyl chloride product is possible. Otherwise, mixtures of alkyl chloride products will be formed. On the other hand, bromination is more selective. It proceeds through only the most stable carbon-centered radical, yielding predominantly one product. If a stereocenter is formed during the reaction, both configurations result at that center. This description of the radical halogenation of alkanes was an excerpt from Introductory Organic Reaction Mechanisms, a color-coded approach to arrow pushing. If you found this video helpful, you may be interested in the complete book, which is available in ebook format from Scribd, or in paperback format from Amazon, as well as in paperback at a discounted price from Lulu.